Yeah, so we're going to also extend the idea of linearization to this three-dimensional context here. If I've got a function f of x, y, the linearization, remember that linearization for our two-dimensional version of this was, it was just the tangent line. That's really what the linearization was. It was L of x was f at a plus f prime at a times x minus a. If I remember right there. But what that amounted to was, this was just the tangent line at a. Okay, that's what that was. Same thing here. The linearization at the point A, B, so they're going to use, instead of A, just A, we've got to add a B in there. And then, of course, the Z would be whatever is that gives you out of fxy there. Well, it's pretty much the two variable counterpart to that. L, so now we've got two variables, x and y, instead of just one. It's going to be f of AB plus, now, again, the complication is, this, we just have one derivative, if you will. Well, since you got a two variable, you got two partial derivatives, so it's f partial with respect to x at AB times x minus a plus partial f with respect to y at AB times y minus. Just really extends it. If you think about it, this, again, what this is right here, that's just going to be your, basically your tangent plane. Remember what we just talked about there, z minus z0 equals partial derivative with respect to x, x0, y0 times x minus x0 plus f partial with respect to y, y minus y0. Oops. Okay, so that was our tangent plane. But do you see what we did here? Instead of saying x0, y0, we're saying a and b, right? And then the z0 is f of ab. And then really they just move that term over. You just move this term over and get, so it's the tangent plane. That's what this is, okay? The linearization is just renaming it, repackaging it, calling it linearization. And the reason it's done is because what this does is it takes this function, linearizes it, that's even a word, but just like we talked about the two-dimensional, if we've got a curve, the linearization takes and linearizes that curve, so it make it into a line, and now it's only good, so to speak, around that particular x value, whatever it is. Well, same thing can be done with a tangent plane. This gives me a good approximation, so this is a good approximation of your function values, z values, around this AB point. So it's the linear approximation or tangent plane approximation. All right. Yeah, let me write that, because, so what we're saying, another way to say that is f of xy is approximately equal to L of xy for f around or at a b. Something like that. It's just that we're dealing in 3 dimensions here, so we got to talk about planes instead of lines. Anyway, all right. Let's find one of those then. So find the linearization. Of f xy equals x squared y cubed at, and keep it sort of simple there, 1, 1, 1. So L of xy is linearization. It is, all right, so it's f of AB, so it'll be f. This is our A, this is our B. We're just calling it A and B instead of x0, y0. So f of AB, so I need to do f of 1, 1. That's easy. Plus partial of f with respect to x of 1, 1. Then times x minus 1. And then plus partial of f with respect to y at 1, 1 times y minus b, which is 1 also. So we can figure out those things. We got it. Like I said, f of 1, 1 is easy. Plug in x to be 1, y to be 1, you got 1. F partial with respect to x, what we got there? 2xy cubed. So evaluate that at 1, 1, you got 2. So 2 times x minus 1. Partial of f with respect to y, well, partial of f with respect to y, it'd be 3x squared y squared. And I made it real easy on myself here. 1, 1, 1, so x is 1, y is 1, so that's just 3. And then, yeah, they usually clean that up just a little bit. Simplify, distribute, and then simplify. 2x plus 3y minus 4, linearization. Now, may be, or one possibility for using this. Remember, one of the neat little, you know, when we were doing linearization, one of the linearizations we talked about was if you got y equals, f of x equals sine of x, the linearization at 0, where a is 0, the L of x turned out to be x. In other words, to approximate, you can approximate sine of x around 0 with just the x. So like sine of 0.9, or sorry, 0.1, 0.9 may be a little too far out, but the sine of 0.1, based on this linearization, is about 0.1. So you can approximate, instead of having to, you know, do I know what sine of 0.1 is? I don't, you know, depends on the calculator, but without using a calculator, I don't know what that is. But by this approximation, I can tell you it's 0.1, okay? You see what I'm saying? Well, you can do the same thing with these, all right? So let's say I was wanting, let's approximate f of 0.9, 0.9 using our linearization here. right? Because 0.9, that's close to 111. Again, without, I mean, punching in a calculator is not that hard, but without a calculator, that's, you know, not too bad, but it would take a little bit of work. But since this point is close to that, this linearization it'll give me a pretty good approximation. So, so this, what we're saying is f of 0.9, comma 0.9. It's going to be approximately equal to L of 0.9, comma 0.9, which is 2 times 0.9 plus 3 times 0.9 minus 4, 1.8 plus 2.7 minus 4. Yeah, I can do that a lot easier than I can do the squaring and cubing thing, so I'm good with this. All right, what is that? 3.4 is 0.5, isn't it? I did that right? That's 4.5, right? Minus 4 is 0.5. I did that down, so f of 0.9, it's going to be about 0.5. What is it? It's actually. Let's calculate the exact. All right. So 0.9 squared times 0.9 cubed exactly is 0.59. It's pretty close. Anyway, all right.
Work on the tests.